What if I told you there are structures lurking in the depths of space so enormous they make entire galaxies look like specks of dust? We're not talking about black holes or superclusters. We're talking about something far grander, something almost incomprehensible in its scale. Picture this: colossal walls of galaxies stretching across billions of light years, threading through the cosmos like invisible veins, binding the universe together in ways we're only beginning to understand. These are the Great Walls of galaxies, the largest known structures in existence, and their sheer size defies everything we thought we knew about the limits of space. Now, let that sink in for a moment. A single one of these cosmic behemoths can contain thousands of galaxies, each with hundreds of billions of stars, all woven into an intricate web so vast it would take a spacecraft millions of years just to cross a fraction of it. And yet, here's the strangest part: we can't even see most of them directly. These walls are like ghosts, their presence revealed only by the galaxies that trace their outlines, like fireflies caught in an endless dark net. How does something this immense come to exist? What force could possibly sculpt the universe on such a mind-bending scale? That's the mystery we're diving into today. This isn't just a story about distant celestial oddities, it's a journey into the very fabric of reality, a chance to witness the universe's most breathtaking architecture. What we'll uncover challenges our understanding of physics, time, and even the nature of existence itself. So buckle up, because by the end of this exploration, you'll never look at the night sky the same way again. The scale of these structures isn't just big, it's beyond anything you've ever imagined. And the best part, this is just the beginning of what's out there. Think of the universe not as a collection of isolated galaxies floating in empty space, but as a sprawling, interconnected network, an immense cosmic web where everything is linked by invisible threads of gravity. The Great Walls of galaxies aren't just random clusters. They're the densest knots in this web, the grand intersections where filaments of dark matter and gas converge, pulling galaxies together like pearls on a string. This web isn't static, it's alive, constantly evolving, shaped by forces that began their work just moments after the Big Bang. Here's how it happened. In the earliest moments of the universe, tiny fluctuations in density, ripples no larger than quantum fluctuations, were imprinted on the fabric of space-time. As the cosmos expanded, gravity amplified these ripples. Regions with slightly more matter pulled in more gas and dark matter, growing denser over billions of years, while emptier regions stretched into vast cosmic voids. The result, a delicate balance where matter clumped into long, winding filaments, with galaxies forming along them like dew on a spider's web. The Great Walls are where these filaments cross, creating staggering superstructures that can span hundreds of millions of light years. What's truly mind-blowing is how fragile this process was. If those initial density fluctuations had been even slightly weaker, galaxies might never have formed at all. If they'd been stronger, matter might have collapsed into one enormous black hole. Instead, we got this intricate cosmic tapestry, a perfect storm of physics and chance that gave birth to everything we see. And here's the kicker: we're only seeing a fraction of it. The galaxies we observe are just the luminous tip of the iceberg, tracing the outline of something far larger and darker. Most of the cosmic web is made of dark matter, an invisible scaffold that guides where galaxies grow. Without it, those towering walls would never have taken shape. So when we stare at these immense structures, we're not just looking at galaxies, we're glimpsing the hidden architecture of the universe itself. These so-called Great Walls aren't solid barriers or cosmic fortresses, they're something far more fascinating. Imagine standing in a dense forest at night, holding a lantern. The light only reveals the trees closest to you, but you can still trace the shape of the forest by how those trees cluster together. That's how astronomers detect these structures, not by seeing the walls themselves, but by mapping the galaxies that outline them like luminous pins on a dark canvas. Each wall is actually a vast sheet of galaxies, a sprawling metropolis of stars and dark matter stretching across hundreds of millions of light years, so large that even light, the fastest thing in the universe, would take an unimaginable length of time to cross one. To grasp their scale, let's shrink the cosmos down to something familiar. If our solar system were a grain of sand, the Milky Way would be a beach ball-sized swirl of sand grains, and a single Great Wall would dwarf that beach ball to the size of Mount Everest. These aren't just big structures, they redefine what big even means. The Sloan Great Wall, one of the most famous examples, spans roughly 1.5 billion light-years. That's about 1/60th the observable universe, a single structure so immense it challenges our theories about how matter should be distributed across space. What makes these walls even stranger is how they defy expectations. According to our best models of the universe, matter should be spread relatively evenly at the largest scales, like ink diffusing in water. But these walls are more like ink congealing into thick strands, proof that gravity's pull can create staggering imbalances over cosmic time. They're not just collections of galaxies, they're gravitational fingerprints, revealing where dark matter's invisible grip has sculpted the universe into its most jaw-dropping forms. And the most humbling thought, however grand they seem, these walls might just be the local neighborhoods of something even larger, filaments in a web we've only begun to trace. It all started with a simple question. If we could step back far enough, what would the universe really look like? In the late 1980s, astronomers Margaret Geller and John Huckra set out to answer that question in a way no one had before. Armed with painstaking redshift surveys, a technique that measures how fast galaxies are moving away from us by stretching their light, they began mapping slices of the cosmos, plotting thousands of galaxies in 3 dimensions. What they found would shatter the old assumption that galaxies were scattered randomly like stars in the night sky. Instead, they uncovered something breathtaking, a colossal, woven tapestry of galaxies stretching across the heavens, a structure so vast it earned the name the Great Wall. This wasn't just another cluster or supercluster, it was a cosmic mountain range, a towering ridge of galaxies spanning over 500 million light-years, dwarfing anything astronomers had ever documented. The discovery sent shockwaves through the scientific community. Up until then, the prevailing view was that matter was spread relatively evenly throughout the universe. But the Great Wall revealed a truth far stranger, that galaxies were organized into enormous, interconnected sheets, separated by vast empty voids. It was like peeling back the curtain on the universe and finding it wasn't a scattered sea of islands, but an intricate, woven lattice. The CfA2 Great Wall, as it came to be known, wasn't just a cosmic oddity, it was a revolution. It proved that the universe had structure on scales no one had imagined, forcing scientists to rethink everything from galaxy formation to the role of dark matter. Geller and Huckra's work didn't just map a single wall, it opened a new window into cosmology, revealing that these vast networks were the rule, not the exception. Yet for all its grandeur, their discovery was almost missed. The Great Wall didn't leap out in some dramatic, cinematic moment. It emerged slowly, painstakingly, one data point at a time. It took meticulous observations, careful plotting, and above all, the willingness to question long-held assumptions. That's the real lesson here. Sometimes the biggest revelations come when we dare to look at the universe from a new angle and let it show us just how much we still have to learn. When astronomers first laid eyes on the CfA2 Great Wall, they weren't just looking at a cluster of galaxies, they were staring at a cosmic anomaly that shouldn't have existed. This gargantuan structure, stretching 500 million light-years across and packed with over 10,000 galaxies, was more than just a record breaker. It was a direct challenge to everything science thought it knew about the universe's large-scale structure. Picture a sheet of galaxies so vast that if you traveled at light speed from one end to the other, you'd be making that journey for longer than multicellular life has existed on Earth. The real shock wasn't just its size, it was what it implied. Before this discovery, most cosmologists assumed matter was distributed relatively evenly across the cosmos, like sprinkles scattered on a cupcake. But the CfA2 wall revealed something radically different. Galaxies weren't randomly dispersed. They clumped together in enormous, interconnected sheets separated by voids so empty they'd make the deepest corners of our solar system seem crowded. It was as if the universe had built a honeycomb on a scale so massive human intuition couldn't even process it. This discovery didn't just add a new entry to the catalogue of cosmic wonders, it rewrote the rulebook. Suddenly, scientists had to grapple with questions they hadn't even thought to ask. How could gravity alone create structures this enormous? Why did galaxies prefer these dense walls instead of spacing themselves evenly? The prevailing models of cosmic evolution had no ready answers. The wall's sheer existence hinted at gaps in our understanding of dark matter's role, the influence of primordial quantum fluctuations, and even the fundamental limits of how quickly structures could grow after the Big Bang. What made the CfA2 wall even more fascinating was its ghostly nature. Unlike a mountain range you could point a telescope at, this structure was invisible in the traditional sense. Its discovery relied entirely on redshift surveys tracking how the light from thousands of galaxies shifted as they moved away from us, then using that data to reconstruct their three-dimensional positions. It was cosmic detective work, revealing patterns no one had thought to look for before. The impact was immediate and profound. This wasn't just about finding a big thing in space. It was about realizing the universe organizes itself in ways that defy simple explanation. If walls like this could exist, what else was out there, hidden in the darkness? The CfA2 Great Wall didn't just expand our map of the cosmos. It shattered the old one and forced us to start drawing a new one from scratch. And as we'll see, this was just the first thread in a tapestry far more intricate than anyone had imagined. Just when scientists thought they'd grasped the limits of cosmic scale, the universe delivered another shock, one that made the CfA2 Great Wall look almost modest by comparison. In 2003, data from the Sloan Digital Sky Survey revealed a structure so vast, it stretched the very definition of what astronomers thought was possible. Meet the Sloan Great Wall, a mind-numbing filament of galaxies spanning 1.4 billion light-years, a structure so colossal, light leaving one end when dinosaurs still roamed Earth would only now be reaching the other side. This wasn't just another wrinkle in the cosmic web, it was a full-blown revolution. The Sloan Wall's sheer size seemed to defy the cosmological principle, a bedrock idea stating that, on large enough scales, the universe should look roughly the same in every direction. Yet here was a behemoth that occupied nearly 3% of the observable universe's diameter, throwing that assumption into doubt. Imagine shuffling a deck of cards and finding all the aces lined up in a perfect row statistically. It shouldn't happen. That's the scale of the anomaly astronomers were staring at. What made the Sloan Wall even more perplexing was how it formed. According to cosmological models, structures this enormous simply shouldn't have had enough time to assemble after the Big Bang. Gravity works slowly, and for galaxies to clump into a sheet this vast, the process would have needed a head start, hinting that those primordial density fluctuations we mentioned earlier might have been far more dramatic than we thought. Some theorists even wondered if the wall was a statistical fluke, a chance alignment of smaller filaments that only looked connected from our vantage point. But the Sloan survey's razor-sharp data left little room for doubt. By mapping over 200,000 galaxies with unprecedented precision, it revealed the wall's true anatomy, not a random jumble, but a coherent, gravitationally bound structure threading through the void like a cosmic backbone. Its galaxies weren't just neighbors, they moved in sync, tugged by the same invisible rivers of dark matter. here's where things get even stranger. The Sloan Wall isn't alone. Since its discovery, astronomers have spotted even larger candidates like the South Pole Wall and the Hercules Corona Borealis Great Wall, some stretching over 10 billion light-years. Each one chips away at the notion that the universe is uniform at grand scales, suggesting instead that we're living inside a cosmic fractal, where patterns repeat no matter how far you zoom out. And if that's true, the walls we've found so far might just be the first threads of a tapestry we're only beginning to unravel. The Sloan Great Wall didn't just break records, it broke expectations, forcing us to confront how little we truly understand about the universe's architecture. It's a humbling reminder that every time we think we've seen the biggest, the cosmos has a way of showing us we've barely scratched the surface. The Great Walls of Galaxies don't just break records, they break rules. According to one of cosmology's foundational ideas, the cosmological principle, the universe should look more or less the same no matter where you're standing. On large enough scales, matter ought to be distributed evenly like flour stirred into batter. But these walls, with their sprawling, galaxy-packed sheets stretching over billions of light-years, throw that assumption into chaos. They're not just outliers, they're cosmic rebels defying what we thought was possible. Take the Sloan Great Wall. At 1.4 billion light-years long, it's not just big, it's statistically improbable. Cosmologists have a term for the upper limit of how large structures should grow, the end of greatness. Beyond a certain scale, the universe's expansion should overpower gravity's pull, preventing matter from clumping together into anything larger than a few 100 million light-years across. Yet here we are, staring at walls that laugh in the face of that limit. It's like finding a single snowflake the size of a continent, something so wildly out of proportion. It forces us to question whether we've misunderstood the recipe of the cosmos itself. So how did these structures slip past the rules? One possibility is that the early universe's density fluctuations were far more dramatic than our models predict. Imagine blowing up a balloon with tiny imperfections. If those flaws were just slightly deeper, the balloon might form ridges and folds as it expands. In cosmic terms, those deeper wrinkles could have given gravity a head start, allowing matter to collapse into vast sheets before the universe's expansion could smooth them out. But there's another twist. Our models rely heavily on dark matter's behavior, and if we've gotten that wrong, all bets are off. Maybe dark matter interacts in ways we haven't accounted for, or perhaps there's an undiscovered force amplifying gravity on unimaginable scales. Some theorists even toy with the idea that these walls are relics of a more exotic early universe, cosmic scars from processes we can't yet explain. Here's the kicker: the closer we look, the more walls we find. Each new discovery pushes the boundaries of what large-scale structure even means. If the universe were truly uniform, these behemoths shouldn't exist. Yet they do, and that's the mystery that keeps astronomers up at night. The Great Walls aren't just curiosities, they're clues, hinting that the universe's grandest blueprints might still be written in a language we're only beginning to decipher. If you tried to build a bridge this enormous out of the galaxies we can see, it would collapse instantly. The stars and gas we observe simply don't have enough gravity to hold these vast walls together. So what's keeping them from flying apart? The answer lies in the universe's best-kept secret: dark matter, an invisible scaffolding weaving through the cosmos, holding everything in place. Think of it as the cosmic glue we can't see, but without it, those majestic galaxy walls would dissolve into chaos. Scientists estimate that dark matter makes up roughly 85% of all matter in the universe, outweighing the visible stuff we know by a staggering margin. It doesn't emit, reflect, or absorb light, which means we can't observe it directly, but we know it's there because of the way it tugs on galaxies with its gravitational pull. Picture a sheet of black ice stretching across the universe, invisible to the eye, yet strong enough to bend the paths of stars and galaxies like marbles rolling across its surface. That's the silent force shaping the Great Walls, drawing galaxies into vast, shimmering webs along its hidden contours. Here's how it works. After the Big Bang, dark matter began clumping together first, forming an intricate network of gravitational wells, cosmic potholes where ordinary matter could collect. Gas and dust poured into these wells, eventually igniting into stars and galaxies along the densest filaments. Over billions of years, these strands grew thicker, knitting themselves into the colossal walls we see today. The galaxies we observe are just the glittering surface, tracing the outlines of something far larger and darker beneath. Mapping this unseen architecture is one of modern astronomy's biggest challenges. Since dark matter won't reveal itself through light, scientists have to get creative. One technique relies on gravitational lensing, the way dark matter bends the light from distant galaxies as it passes through, distorting their shapes like a funhouse mirror. By analyzing these distortions, researchers can reconstruct the hidden mass, revealing where dark matter clumps and flows. Another method tracks the motion of galaxies themselves. Just as leaves floating on a river's surface show the current beneath, galaxies moving in unexpected ways betray the presence of dark matter's pull. Some of the most detailed maps come from projects like the Dark Energy Survey and the Euclid Space Telescope, which scan vast swaths of the sky to trace dark matter's ghostly silhouette. What they've found is astonishing. These walls aren't just random gatherings of galaxies. They're cosmic freeways with dark matter acting as the underlying grid, guiding galaxies into place with invisible precision. And the deeper we look, the stranger it gets. Some filaments appear denser than predicted, as if dark matter itself has a hidden structure we've yet to decode. The irony is striking. The largest structures in the universe are shaped by something we can't even see, their true form written in a language of gravity and motion. Every time we uncover a new Great Wall, we're not just discovering galaxies, we're reading the fingerprints of dark matter, the silent architect behind the cosmos' grandest designs. And the more we learn, the clearer it becomes. To understand the universe's greatest wonders, we must first learn to see the invisible. The Great Walls of galaxies might steal the spotlight, but they're not solitary giants. They're connected by something even more mesmerizing. Picture the universe's largest highways, threads of galaxies and dark matter so slender yet so vast, they make the Milky Way look like a speck on a cosmic tightrope. These are the filaments, the delicate arteries threading the cosmos, some stretching over 500 million light-years from one wall to another, weaving the universe into a single, interconnected web. Simulations of the cosmic web reveal these filaments as shimmering strands, like the finest spider silk stretched across unimaginable distances. Each one is a river of galaxies and gas, flowing along invisible currents of dark matter. Imagine standing at the edge of one, looking down its length. You'd see galaxies strung like beads, each one pulled into line by gravity's unrelenting grip. But here's what's truly astonishing. Despite their delicate appearance, these filaments are anything but fragile. They're the backbone of the cosmic web, the channels through which galaxies travel, collide, and even merge over billions of years. What's wild is how these filaments form. In the early universe, dark matter began clumping first, drawing ordinary matter into its gravitational embrace. Over time, the densest regions became the Great Walls, while the thinner stretches remained as filaments, cosmic bridges between titanic structures. Some are so vast, they could connect our local supercluster to neighbors we've yet to discover. And just like rivers on Earth, they're not static. Galaxies slide along them, pulled by the irresistible tug of larger clusters at their endpoints, in a dance that's been unfolding since the dawn of time. The most detailed simulations, like those from the Illustris TNG project, show these filaments in breathtaking detail. Gas flows through them like water through a pipe, feeding the growth of galaxies at their intersections. Shock waves ripple along their lengths, heating matter to millions of degrees so hot They glow in X-rays, revealing hidden pathways we'd never see with ordinary telescopes. It's like turning on black lights in a dark room and suddenly seeing the ink trails of some grand, invisible design. But filaments aren't just cosmic eye candy, they're proof of the universe's dynamic nature. Without them, galaxies would be isolated islands adrift in emptiness. Instead, they're linked, part of a vast circulatory system where gas, stars, and even entire galaxies migrate from walls to nodes, shaping the large-scale structure of everything we see. And just like the Great Walls, these filaments defy expectations. They shouldn't be so long, so coherent, or so abundant, yet there they are, threading the void with quiet precision, reminding us that the universe's grandest designs often lie in the spaces between. If you zoomed out far enough, even our home supercluster, the massive Laniakea, would shrink into nothing more than a single brick in one of these staggering galactic walls. That's right, the structure containing our Milky Way, along with 100,000 other galaxies spanning over 500 million light-years, is just one piece of something far grander. The Laniakea supercluster isn't a solitary titan, it's a thread woven into the fabric of a wall so immense, it redefines our place in the cosmos. Picture Laniakea as a bustling metropolis, with galaxies flowing along its gravitational streets like commuters drawn to a downtown core. At its heart lies the Great Attractor, a mysterious region pulling everything toward it with the force of a quadrillion suns. Yet for all its grandeur, Laniakea is merely a neighborhood within the larger Pisces-Cetus supercluster complex, a sprawling galactic wall that stitches together multiple superclusters into a single, coherent sheet. This wall isn't just bigger, it's a different category of existence altogether, a structure where even superclusters become subunits in a hierarchy we're only beginning to map. The scale here is dizzying. While Laniakea's galaxies orbit a shared center of gravity, the wall they're embedded in operates on a whole other level. Imagine standing in a single room of a skyscraper, then realizing your entire building is just one pixel in a city skyline stretching to the horizon. That's the leap we're making from superclusters to walls. These walls aren't just collections of galaxies, they're the universe's scaffolding, the frameworks upon which everything else is built. What's fascinating is how these walls form. Superclusters like Laniakea don't simply drift into place, they're funneled there by dark matter's invisible currents, sliding along filaments until they pile up like cosmic flood debris against these vast gravitational levees. Over billions of years, mergers and collisions reshape them, but the walls endure, growing ever larger as the universe expands. And here's the humbling part. If walls are cities, then superclusters like ours are just suburbs, important, but far from the center of the action. This reshapes how we understand our galactic home. We often think of the Milky Way as part of something local, like the Virgo cluster or Laniakea. But the truth is, we're nested within structures so vast they make even these colossal groupings feel small. The universe isn't just hierarchical, it's fractal, with patterns repeating at every scale, and that realization changes everything. What we once called large is just a stepping stone to something grander, a reminder that in the cosmic web, there's always a bigger picture waiting to be seen. Building a universe from scratch isn't just a fantasy, it's science. For decades, astrophysicists have been crafting digital cosmos inside supercomputers, simulating billions of years of cosmic evolution in mere weeks. These aren't simple animations, they're meticulously coded virtual universes governed by the same laws of physics that shape our reality. The goal, to see if our theories about dark matter, galaxy formation, and large-scale structure hold up when pitted against the real thing. And when it comes to the great walls of galaxies, the results are as awe-inspiring as they are humbling. Take the illustrious TNG project, one of the most advanced simulations ever created. It starts with a digital soup of particles representing dark matter and gas. Then lets gravity, hydrodynamics, and other forces run wild over 13.8 billion simulated years. The outcome, a virtual universe eerily reminiscent of our own, complete with swirling galaxies, glittering clusters, and, yes, vast, weaving walls of galaxies stretching across the void. But here's where it gets fascinating. When researchers compare these simulated walls to real ones like the Sloan Great Wall, the match isn't perfect. The simulations get the broad strokes right, the web-like structure, the clustering of galaxies along filaments, but the details often diverge in ways that keep scientists up at night. For instance, Illustrious predicts walls should be more evenly distributed with fewer extreme outliers. Yet the real universe seems to love breaking records, producing titanic structures that defy statistical expectations. The Sloan Wall's sheer size, for example, appears in less than 5% of simulations, a cosmic roll of the dice that our universe somehow hit. Then there's the matter of voids. Simulations tend to create emptier, smoother gaps between walls, while actual observations reveal voids that are lumpier, as if something, perhaps dark matter's quirks or primordial turbulence, stirred the pot more violently than models account for. These mismatches aren't failures, they're clues. Every discrepancy between simulation and reality forces scientists to revisit their assumptions. Maybe dark matter interacts with itself in ways we haven't modeled. Maybe the early universe's density fluctuations were more dramatic than we thought. Or perhaps there's an undiscovered force nudging cosmic structures into unexpected shapes. Simulations like Millennium, Eagle, and Cosmic Dawn are tackling these questions, each refining the recipe with new physics or higher resolution. Some even suggest that quantum effects in the universe's first moments left scars on spacetime that later grew into these colossal walls, a twist no one saw coming. But the real triumph of these simulations isn't just in their predictions, it's in their power to surprise us. Recently, one simulation accidentally revealed a phenomenon called galactic conveyor belts, where galaxies migrate along filaments at speeds far higher than expected, like commuters on a cosmic bullet train. When astronomers checked telescope data, they found the same thing happening in real galaxy clusters. It's a reminder that even our most advanced models are still just sketches of a reality far richer and stranger than we've imagined. So where does that leave us, staring at two reflections of the cosmos, one born from silicon and code, the other from 12 billion years of unscripted cosmic history? The differences between them aren't just glitches, they're breadcrumbs leading to deeper truths. With every simulation update, every new sky survey, we inch closer to understanding why the universe builds these walls, and what they're trying to tell us about the hidden laws that shaped everything we see. The day simulations and reality match perfectly might be the day we've finally cracked the universe's code. Until then, the gaps between them are where the real magic happens. Just when astronomers thought they'd seen the limits of cosmic scale, along came a claim that shattered every record and nearly every assumption. In 2013, a team of researchers studying gamma-ray bursts, the universe's most violent explosions, announced the discovery of something so vast it seemed impossible. They called it the Hercules Corona Borealis Great Wall, a structure purportedly stretching 10 billion light-years across nearly 1/10 the observable universe. If real, it wouldn't just be the largest known structure, it would rewrite the rules of cosmology itself. But almost immediately, the pushback began. The controversy wasn't just about size, it was about definition. Unlike the Sloan Great Wall or CfA2, which were mapped using galaxies as signposts, the Hercules Corona Borealis claim relied on gamma-ray bursts. These fleeting, high-energy flashes are thought to mark the deaths of massive stars, and the team argued that an unusual concentration of them in one patch of sky traced the outline of an unfathomably large wall. The logic was bold. If gamma-ray bursts occur where galaxies are most active, then a dense cluster of them might reveal a hidden superstructure. The problem: gamma-ray bursts are rare, capricious, and spread thinly across cosmic time. Critics argued that what looked like a wall could just be a statistical fluke, a random alignment of explosions scattered over billions of years, not a coherent structure bound by gravity. The debate cut to the heart of how we define cosmic architecture. Traditional walls are gravitationally connected galaxies moving together, anchored by dark matter. But gamma-ray bursts don't directly measure gravity's pull. They're cosmic fireworks signaling star-forming regions without proving those regions are linked. Imagine trying to map a mountain range using only lightning strikes. If bolts frequently hit one area, does that mean there's a mountain beneath them or just stormy weather? That's the uncertainty plaguing the Hercules Corona Borealis claim. Without galaxies or dark matter to confirm its shape, the wall remained a tantalizing maybe. Yet even as skepticism grew, the discovery sparked a deeper conversation. If structures this colossal could exist, how would we even recognize them? The Hercules Corona Borealis debate forced astronomers to refine their criteria, distinguishing between true walls, gravitationally bound and dynamically connected, and chance alignments that only look like structures from our vantage point. It also highlighted a thorny truth: the farther out we peer, the harder it becomes to separate signal from noise. At 10 billion light-years, we're seeing the universe in its youth, a time when matter was clumpier and less evenly spread. What looks like a wall could just be a snapshot of the cosmos mid-assembly, before expansion smoothed things out. The controversy's legacy isn't a definitive answer but a lesson in cosmic humility. Every time we think we've grasped the universe's scale, it throws us a curveball, a reminder that our tools and definitions are works in progress. Whether the Hercules Corona Borealis Great Wall is real or not, its shadow looms large, challenging us to ask not just how big is it, but how do we know? And in that question lies the real frontier of discovery. Staring up at the night sky, what we see is a flat canvas, a two-dimensional tapestry of stars, galaxies, and cosmic light. But the universe isn't flat. It's a depthless ocean with layers upon layers stretching back billions of years. So how do astronomers take that flat image and reconstruct the sprawling three-dimensional cosmos hidden within it? The answer lies in one of their most powerful tools, redshift, the cosmic barcode that reveals not just where objects are, but how far away they exist in the vastness of time and space. Here's how it works. When light from a distant galaxy travels across the expanding universe, its wavelengths stretch like taffy, shifting toward the red end of the spectrum. The farther the light travels, the more extreme this redshift becomes. By measuring this shift, astronomers can calculate a galaxy's distance from us with remarkable precision. It's like hearing an ambulance siren change pitch as it speeds away. The sound stretches, telling you whether it's moving closer or farther. Redshift does the same for starlight, turning a flat sky map into a multidimensional model. But redshift alone isn't enough. Imagine standing in a dense forest at night, holding a flashlight that only illuminates the nearest trees. You might see a cluster of trunks and assume they're connected, but are they really part of the same grove, or just trees that happen to line up from your perspective? That's the challenge astronomers face when mapping structures like the Great Walls. They use redshift surveys, massive projects like the Sloan Digital Sky Survey, to measure thousands of galaxies at once, plotting their positions in 3D space. The result is a cosmic point cloud, a scatter of galaxies that slowly reveals patterns, clusters here, filaments there, and vast arching walls threading through the darkness. The real test is distinguishing true structures from chance alignments. Just because two galaxies appear close together in the sky doesn't mean they're physically linked. One might be a foreground object while the other lurks billions of light years behind it. To confirm a wall's existence, astronomers look for coherent galaxies moving together, bound by shared gravity, their redshifts clustering in ways that betray their connection. It's like watching commuters in a train station. If everyone's rushing in different directions, it's just a crowd. but if dozens move in sync, they're likely part of the same group. Even then, uncertainties linger. Dust clouds, telescope limitations, and the sheer scale of these structures can obscure the truth. Some walls might be mirages, illusions created by our limited perspective. Others could be fragments of something larger, their full shape still hidden. That's why modern surveys go beyond redshift, incorporating velocity measurements, gravitational lensing distortions, and even simulations to cross-check their maps. The goal isn't just to see deeper, it's to see truer, peeling back layer after layer until the universe's hidden architecture finally comes into focus. What emerges is a revelation. The night sky isn't just a scattering of lights. It's a dynamic, three-dimensional web, its threads woven across billions of years. And every new technique we develop brings us closer to reading that web like a cosmic blueprint, one redshift, one galaxy, one wall at a time. The echoes of creation are still ringing through the cosmos, etched into the very fabric of the Great Walls themselves. To understand how these colossal structures came to be, we need to rewind to the universe's first 380,000 years, a time when space wasn't empty, but filled with a seething, opaque plasma so dense, light couldn't travel more than a fraction of an inch before bouncing off particles. In this primordial soup, gravity pulled matter inward while radiation pressure pushed it outward, creating ripples of compression and rarefaction that surged through the plasma like sound waves through air. These weren't ordinary sound waves, they were cosmic tsunamis, racing outward at half the speed of light, imprinting their rhythm on the newborn universe. When the cosmos finally cooled enough for atoms to form, an event we call recombination, those ripples froze in place, leaving concentric rings of matter like fossils in the sky. Fast forward billions of years, and those rings became the seeds of the Great Walls, their spacing preserved like the grooves of a vinyl record. Astronomers call these imprints baryon acoustic oscillations, and they're one of the most powerful tools we have for measuring the universe. Here's why: the original wavelength of those sound waves was determined by physics so fundamental. It's practically the same everywhere, about 500 million light-years from peak to peak. That makes them a standard ruler scribed across the heavens, allowing scientists to gauge cosmic distances with astonishing precision. When we map galaxy walls today, we're seeing those ancient oscillations writ large. The walls didn't form randomly. They followed the blueprint laid down by those primordial sound waves, clustering at predictable intervals like beads on a string. By measuring how much these spacings appear stretched or compressed across different eras, astronomers can track how the universe has expanded over time, revealing hidden forces like dark energy that are stretching space itself. It's as if the universe handed us a yardstick at the dawn of time, and we're only now learning how to read it. But the real magic lies in how these oscillations solve two mysteries at once. First, they explain why great walls tend to have similar scales, their sizes trace back to those early sound waves. Second, they act as cosmic calibration marks, letting us measure expansion rates independent of supernova or other methods. When different techniques agree, it's a triumph. When they disagree, as they occasionally do, it hints at gaps in our understanding, like missing ingredients in dark energy's recipe. Recent surveys like DAISY and Euclid are mapping these oscillations with unprecedented detail, scanning millions of galaxies to reconstruct the universe's expansion history. What they've found is both confirming and confounding. While most measurements align beautifully with our models, some walls appear slightly closer together than expected, as if dark energy's push has changed over time. It's a whisper of something deeper, perhaps evidence that the universe's expansion isn't as uniform as we thought, or that those primordial sound waves carried secrets we've yet to decode. So the next time you hear about a newly discovered Great Wall, remember, its story began with a vibration, a whisper of sound in the newborn cosmos that grew into the largest structures we've ever seen. These walls aren't just cosmic landmarks, they're time capsules, preserving the echo of creation itself. And with every survey, every map, we're listening closer, tuning our instruments to the universe's oldest song. The story of the Great Walls begins not with a bang, but with a whisper, faint ripples in the newborn universe slowly knitting themselves into the largest structures we've ever seen. Around 2 to 3 billion years after the Big Bang, when the cosmos was just a fifth of its current age, the first tendrils of these walls started taking shape. Picture an unseen hand drawing invisible lines across the sky, tracing paths where dark matter's gravity would eventually pull galaxies into alignment. Back then, these proto-walls were mere shadows of their future selves, thin, wispy filaments where gas and young galaxies huddled together in the darkness. What transformed these fragile threads into the colossal structures we see today? The answer lies in one of the universe's most relentless forces, time. Over billions of years, gravity worked like a cosmic loom, weaving those early filaments into denser sheets. Galaxies didn't just stay put, they migrated along these invisible highways, drawn toward intersections where filaments crossed. Collisions and mergers became inevitable, with smaller galaxies cannibalizing each other to form the giant ellipticals we often find at the hearts of walls today. It's a process that's still unfolding. Even now, the Milky Way is hurtling toward the Andromeda Galaxy at 200,000 miles per hour, destined to merge in a few billion years. On the scale of great walls, such events are routine, just another stitch in the tapestry. But gravity isn't the only architect here. Around 5 billion years ago, a new player entered the scene, dark energy. As the universe expanded, this mysterious force began accelerating the cosmos' growth, stretching space itself like taffy. At first, its effects were subtle, a gentle tug opposing gravity's pull. But over time, dark energy started winning the cosmic tug-of-war, pushing galaxies apart even as gravity tried to bind them together. The result, walls kept growing, but more slowly, their edges diffusing as galaxies at the fringes were carried away by the expanding void. Some simulations suggest the largest walls may have stopped growing altogether, frozen in time like fossils of an earlier, more dynamic universe. Yet for all their grandeur, these structures aren't permanent. Peer far enough into the future trillions of years from now, and dark energy's pull will likely tear the walls apart entirely, isolating galaxies in an ever-darkening cosmos. It's a humbling thought. The same forces that built these titanic structures will one day erase them, leaving no trace behind. But for now, they stand as monuments to the universe's most formative epochs, their layers holding clues to everything from the nature of dark matter to the fate of everything we know. And with every new telescope, we're reading those layers like the rings of a cosmic tree, each one a chapter in the greatest story ever told. Right now, the great walls of galaxies stand as the universe's grandest monuments, but their reign won't last forever. The same force that's stretching the cosmos apart, dark energy, is also writing their eventual obituary. Imagine a tapestry slowly unraveling at the edges, its threads pulled taut until the pattern dissolves into chaos. That's the fate awaiting these colossal structures, not in millions or billions of years, but over timescales so vast they make the age of the universe seem like a blink. The process has already begun. Dark energy's push against gravity is relentless, accelerating the expansion of space itself. Right now, galaxies within walls are still bound together, their gravity strong enough to resist the cosmic tug-of-war. But as expansion accelerates, the space between them widens, stretching the wall's fabric thinner and thinner. Eventually, even the strongest gravitational bonds will snap. Galaxies at the edges will drift away first, like leaves caught in a river's current, their light redshifted into oblivion as space carries them beyond the visible horizon. The wall's cores may hold out longer, clinging together in dwindling clusters, but over trillions of years, even they'll dissipate into the void. Simulations paint a haunting picture of this far future. As dark energy dominates, galaxies outside our local group will vanish from sight, their light stretched beyond detectability. The Milky Way and Andromeda, merged into a single elliptical galaxy, will orbit each other in an ever-darkening sky. The cosmic web, once vibrant with filaments and walls, will fray into isolated knots, each unaware of the other's existence. It's a future so lonely, astronomers call it the Big Freeze, where the universe's temperature approaches absolute zero and star formation grinds to a halt. But here's the twist: the Great Walls might leave ghostly echoes behind. Even as galaxies drift apart, their gravitational waves, ripples in space-time from ancient collisions, could persist, carrying faint whispers of structures long gone. Future civilizations, if they arise, might piece together the universe's lost architecture by studying these tremors, like archaeologists reconstructing a city from scattered bricks. The irony is profound. These walls, born from the universe's most violent beginnings, will meet their end not with a bang but with a slow, silent unraveling. Yet in their dissolution, they offer a final lesson: the cosmos is never static. It's a story written in expansion and collapse, connection and isolation, and the Great Walls are just one breathtaking chapter in an epic far from over. What if the Great Walls aren't anomalies at all, but part of a pattern repeating endlessly across the cosmos? This radical idea comes from fractal cosmology, a theory suggesting the universe's structure mirrors itself at every scale, like a cosmic kaleidoscope where walls, filaments, and voids recur in an infinite cascade. Picture zooming into a snowflake and finding smaller, identical snowflakes within it, then repeating the process forever. That's the fractal universe in a nutshell, a web where every thread contains its own miniature web, stretching from the largest walls down to quantum foam. Proponents of this view point to peculiar observations. When astronomers analyze galaxy distribution, they find clusters nesting within superclusters, which themselves nest within walls, a Russian doll arrangement that hints at deeper layers. Some even argue the Sloan Great Wall's colossal filaments resemble, in miniature, the very threads that connect it to larger structures. If true, it would mean our largest discoveries are just mid-level rungs on an infinite ladder with no true top or bottom. But fractal cosmology isn't the only challenger to the standard model. Another fringe idea, plasma cosmology, suggests electromagnetic forces, not just gravity, sculpt these walls. In this view, interstellar plasma acts like a cosmic glue, channeling galaxies into filamentary flows akin to how electric currents shape neon signs. While mainstream astronomy dismisses plasma's role at such scales, some simulations show it could amplify gravity's effects, creating sharper, denser walls than dark matter alone predicts. Then there's the holographic principle, which posits that our 3D universe might be a projection of information encoded on a 2D surface. In this mind-bending framework, Great Walls could be interference patterns, echoes of deeper physics playing out on reality's fundamental canvas. It sounds like science fiction, but the math behind it emerges from black hole thermodynamics, giving even skeptics pause. The debate boils down to a simple question: are these walls accidents of gravity or signatures of something deeper? Mainstream cosmology leans toward the former, but the outliers raise valid points. If the universe is fractal, why do simulations struggle to replicate structures beyond certain scales? If plasma or holograms play a role, why haven't we detected their fingerprints? Each theory shines light on different cracks in our understanding, reminding us that the cosmos rarely fits neatly into boxes. What makes these alternatives compelling isn't just their audacity, it's their willingness to ask questions the standard model hasn't answered. Maybe the walls aren't anomalies but expected features. Maybe dark matter isn't the only architect, or maybe, just maybe, we're seeing fragments of a blueprint we don't yet have the tools to read. The deeper we look, the clearer it becomes. The universe's grandest structures might be more than marvels. They could be messages waiting for us to decipher their true language. The farther out we peer into the cosmos, the deeper into the past we gaze, and the great walls of galaxies serve as some of the most extraordinary time machines ever conceived. When we observe a wall 10 billion light-years away, we're not just seeing a structure in space, we're witnessing a moment frozen in time, a snapshot of the universe when it was barely a quarter of its current age. These distant walls are cosmic fossils, preserving the conditions of an era when galaxies were younger, hotter, and bursting with star formation, offering us a front-row seat to the universe's most transformative epochs. Take the Hyperion supercluster, a proto-wall discovered in 2018. Located 11 billion light-years away, it's a chaotic nursery of galaxies caught in the act of merging, their collisions igniting starbursts 1,000 times fiercer than anything in our modern Milky Way. Unlike the orderly walls we see nearby, Hyperion's galaxies are crammed together like commuters in a rush-hour train, their motions frenetic, their shapes distorted by violent encounters. This is the universe in its adolescence, raw, energetic, and still figuring itself out. By comparing Hyperion to mature walls like Laniakea, we're essentially flipping through a cosmic family album, watching as gravity sculpts chaos into structure over eons. But the real magic lies in the details. The light from these ancient walls carries chemical fingerprints, traces of hydrogen, helium, and the first heavy elements forged in early stars. In walls like CLJ 1001, a cluster so distant it existed just 2.5 billion years after the Big Bang, astronomers have detected surprisingly mature galaxies already rich with metals. These findings append old assumptions about how quickly galaxies evolved, suggesting some regions of the early universe matured at breakneck speed, like precocious children outshining their peers. It's as if we've stumbled upon a cosmic lost city, a pocket of the ancient universe that defied expectations by growing up too soon. The James Webb Space Telescope has turned these observations into a revolution. With its infrared eyes, Webb peers through dust clouds that once obscured our view, revealing walls like Sears 93,316, a structure so distant its light predates Earth's formation. Here, galaxies glow not with the familiar blue-white of young stars, but with the deep red of ultraviolet light stretched by cosmic expansion, a color shift that tells us exactly how fast the universe was growing when their light began its journey. Each redshift measurement is like a timestamp, allowing us to arrange these walls into a chronological sequence, from the universe's fiery infancy to its structured present. What's emerging is a story of fits and starts. Some walls, like those in the cosmos field, show galaxies maturing in sync, as if following a shared cosmic timetable. Others, like the distant Spiderweb galaxy cluster, reveal bizarre outliers, galaxies that formed too quickly, grew too large, or collapsed into supermassive black holes far sooner than models predict. These exceptions aren't just curiosities, they're clues that the early universe might have been a patchwork of extremes, with some regions racing ahead while others lagged behind. The ultimate prize, catching the moment when the first walls began to form, a time before galaxies existed, when dark matter's tendrils first drew gas into their embrace. Simulations hint that these infant walls should be detectable as faint, diffuse blobs of hydrogen glowing in ultraviolet, a signature Webb is now hunting. If found, they'd be the universe's very first skeletons, the scaffolding upon which everything else was built. Every distant wall we study adds another frame to the cosmic movie, letting us rewind further and further toward the beginning. And with each new discovery, we're reminded that these structures aren't just landmarks in space, they're milestones in time, chronicling the universe's journey from primordial simplicity to the breathtaking complexity we see today. The deeper we look, the clearer it becomes. To understand the cosmos, we must learn to read its walls like the pages of a history book, each one written in the language of starlight and time. If the great walls of galaxies are the towering mountain ranges of the cosmos, then the voids between them are the deepest, darkest valleys imaginable, vast deserts of near-nothingness stretching hundreds of millions of light-years. These aren't just empty spaces, they're cosmic black holes in reverse, regions where gravity lost the battle against expansion, leaving behind bubbles so barren they'd make interstellar space seem crowded. Take the Boötes Void, a spherical chasm over 300 million light-years wide containing just 60 galaxies, a number so low you could fit them all in a single corner of our Milky Way's local group. If you were trapped inside it, the night sky would appear almost pitch black, with only a handful of faint smudges to remind you that galaxies exist at all. What's astonishing isn't just their emptiness, it's how these voids shape the walls themselves. Like yin and yang, voids and walls are locked in a gravitational dance, each defining the other. As voids expand, they push matter into their outskirts, feeding the growth of walls like cosmic tidal forces sculpting sand into ridges. Simulations show this process in eerie detail. As dark energy stretches voids wider, galaxies at their edges get squeezed into ever denser sheets, as if the universe is wringing out a sponge. The result, walls grow sharper and more defined, while voids grow emptier, a feedback loop that's been running for billions of years. But here's the twist, voids aren't completely empty. Scattered across their volumes are void galaxies, lonely outposts that somehow avoided getting swept into the walls. These recluses are unlike their wall-dwelling cousins, smaller, bluer, and slower to mature, like islands untouched by continental currents. Studying them is like finding a single pine tree in the middle of the Sahara. Their very existence hints at untold stories of survival in the cosmos' most hostile environments. Some might be fugitives ejected from wall clusters by ancient collisions. Others could be primordial holdouts, galaxies that formed early and never moved, like hermits refusing to join civilization. The interplay between walls and voids even alters how we see the universe. Light passing through voids gets stretched slightly more than light crossing dense walls, an effect called integrated Sachs-Wolf that subtly warps the cosmic microwave background. It's as if the voids are lenses made of nothingness, bending reality itself, and when astronomers map these distortions, they uncover hidden truths about dark energy's grip on the cosmos. The emptier the void, the stronger its fingerprint, proof that absence can be just as revealing as presence. Yet for all their starkness, voids aren't eternal. Just as walls will one day fray, voids face their own dissolution. As dark energy accelerates expansion, even these vast nothingnesses will stretch until their last tenuous threads of matter snap. The universe's grandest deserts will grow ever lonelier, their boundaries blurring into an all-encompassing haze. But for now, they stand as perfect counterweights to the Great Wall's, proof that the universe's beauty lies not just in what it builds, but in what it leaves behind. The hunt for the universe's grandest structures is far from over. In fact, it's about to leap into hyperdrive. Within the next decade, a new generation of sky-mapping titans will turn their gaze upward, armed with technology so advanced it could rewrite our cosmic atlas. Leading the charge is the Vera Rubin Observatory, perched high in Chile's Atacama Desert. When its 8.4-meter mirror opens its eye to the sky in 2025, it won't just scan the heavens, it'll devour them. Every 3 nights, Rubin's 3.2 gigapixel camera will capture the entire visible southern sky, a feat equivalent to taking 800,000 high-resolution smartphone photos back-to-back. Over 10 years, this relentless survey will catalog over 20 billion galaxies, spotting faint traces of walls previous telescopes missed like footprints in cosmic dust. But Rubin isn't working alone. Orbiting 1 million miles from Earth, the Euclid Space Telescope is already rewriting the rules of cosmic cartography. Unlike Hubble's narrow, deep-field glimpses, Euclid casts a wide net, its infrared eyes scanning 15,000 square degrees of sky to construct the most precise 3D map of the universe ever made. What makes Euclid revolutionary isn't just its reach, but its focus on the invisible. by measuring how dark matter warps the light of distant galaxies. A phenomenon called weak gravitational lensing. It'll trace the hidden scaffolding holding walls together. Early data suggests it might even spot dark walls, structures so faint their galaxies are nearly invisible, detectable only by the way they bend spacetime itself. Then there's DESI, the Dark Energy Spectroscopic Instrument, which isn't just counting galaxies, it's clocking their speeds. Mounted on a telescope in Arizona, DESI 5000 robotic fibers can measure redshift for 5,000 galaxies simultaneously, creating velocity maps that reveal how walls are stretching or compressing as the universe expands. This isn't just about size anymore, it's about motion, dynamics, watching these colossal structures breathe across cosmic time. Already, DESI preliminary data hints at previously unseen superstructures lurking behind the Milky Way's dust clouds, a cosmic blind spot older surveys couldn't penetrate. The real game changer, these projects don't operate in isolation. Rubin's optical scans, Euclid's dark matter maps, and DESI velocity readings will merge into a multidimensional atlas, letting astronomers study walls from every angle at once. Imagine reconstructing a city not just from satellite photos, but from subway routes, traffic patterns, and phone signals. That's the level of insight coming. And with machine learning sifting through petabytes of data, anomalies that once took decades to spot might flash onto screens in real time. What keeps astronomers awake with anticipation isn't just confirming known walls, it's the potential for discoveries that shatter current limits. Could there be walls spanning 5 billion light-years, structures so vast they make the Sloan Great Wall look provincial? Might we find evidence of relic walls, fossilized remnants from before dark energy dominated, preserved like insects in cosmic amber? Or perhaps walls arranged in unexpected geometries, great rings or spirals defying gravity's usual scripts? Every time we've built a better telescope, the universe has responded by revealing something stranger than we dreamed. This time won't be different. The only certainty is that the cosmos has been keeping secrets, and the walls we've found so far might just be the prologue. At some point, the universe itself must draw a line. Even the greatest walls can't stretch forever. But where does physics set that boundary? The answer lies in the cosmic horizon, the ultimate limit set by the speed of light and the age of the universe. No matter how vast a wall appears, it can't exceed the observable universe's diameter of roughly 93 billion light-years. Yet even that staggering figure hides a paradox. Expansion ensures we'll never see the full picture. Every second, galaxies cross beyond our horizon, their light fading into unreachability before it can reach us. The largest structures we detect are mere glimpses of what might exist just out of view. Take the hypothetical final wall, a structure spanning the entire observable universe. In theory, gravity could have woven such a behemoth given infinite time, but dark energy's acceleration makes it impossible. Beyond a certain scale, space expands faster than gravity can pull matter together, freezing growth like a paused video. Current models peg that limit around 1.2 billion light-years, making the Sloan Great Wall a tantalizing hint of cosmic maximums. But here's the twist: walls might appear larger due to perspective. From our vantage point, distant structures can seem connected when they're actually disjointed, like mountain ridges aligning by chance from a single valley. The real shock comes when we ask what lies beyond our horizon. Inflation theory suggests the entire observable universe is a speck in a vastly larger cosmos, where walls could stretch trillions of light-years, structures so immense they make our local giants look like pebbles. We'll never see them, but their gravitational whispers might ripple through space-time, leaving subtle distortions in the cosmic microwave background. Some theorists even speculate that colossal hyperwalls could warp the universe's large-scale curvature, bending reality on scales we can't fathom. Yet the most profound limit isn't size, it's time. The longer we wait, the more the universe's expansion erodes our view. billions of years from now, civilizations may gaze at a sky where no walls remain visible beyond their local cluster, their telescopes capturing only fading echoes of a richer cosmic web. For now, we're living in a golden age of observation, where the universe's grandest blueprints are still legible, but only if we keep looking before the light slips away. Humanity's fascination with cosmic megastructures didn't start with telescopes. It began with storytellers dreaming up impossible walls stretching across the stars. Science fiction has long been obsessed with the idea of artificial or natural barriers on astronomical scales, from the titular ringworld of Larry Niven's classic to the Dyson spheres encapsulating entire stars. But few concepts capture the imagination like the fictional counterparts to the Great Walls of Galaxies structures, so vast they defy both physics and logic, yet feel eerily plausible in the hands of skilled world builders. Take The Wall Around Utopia by Charles L. Harness, where an alien civilization constructs a barrier so immense it encircles an entire star system, not just as a physical shield but as a psychological divide between order and chaos. The novel plays with themes of isolation and control, mirroring how real cosmic walls act as gravitational borders, dictating the flow of galaxies like traffic along an invisible highway. Harness Wall isn't just a setting, it's a character, shaping the destiny of everyone within its shadow. Then there's Alastair Reynolds' The Great Wall of Mars, where the remnants of an ancient conflict have left the red planet encircled by a ruinous barrier, its purpose lost to time. Unlike the orderly filaments of the cosmic web, Reynolds' Wall is a relic of war, a cautionary tale about civilizations reaching too far too fast. The irony is palpable. While real great walls form naturally over billions of years, humanity's fictional counterparts often arise from ambition or folly, built in centuries only to crumble under their own weight. But science fiction's most haunting take might be Lou Sixon's The Wandering Earth, where entire solar systems are rearranged like chess pieces. While not a wall per se, the sheer scale of engineering mirrors the audacity of cosmic filaments, except here, the architects aren't dark matter and gravity, but beings desperate to escape a dying universe. It's a stark contrast to reality, where walls aren't built but born, emerging from primordial chaos without design or intent. What makes these fictional walls so compelling is how they invert reality's rules. In the cosmos, structure emerges from simplicity. In fiction, it's often imposed through will. The Sloan Great Wall wasn't planned, it's a happenstance of quantum fluctuations. But in books like Dan Simmons' Hyperion, the Farcaster network binds worlds with artificial wormhole gates, a deliberate web echoing the cosmic web's connectivity. Both are vast, but one is shaped by chance, the other by choice. Perhaps the most profound difference lies in purpose. Real great walls have none, they simply exist, indifferent to the galaxies they host. Fictional walls, though, are laden with meaning, shields against invaders, prisons for the damned, or monuments to forgotten gods. They reflect our own fears and aspirations, turning astrophysics into allegory. When we imagine a wall spanning light years, we're not just exploring space, we're probing what it means to be small in a universe that dwarfs our dramas. Yet for all their differences, fiction and reality share one truth: scale changes everything. Whether it's the Hercules Corona Borealis Great Wall or the ramparts of a dying empire in a Neil Stephenson novel, these structures force us to reckon with the sublime. They remind us that the universe, real or imagined, doesn't conform to human expectations. It builds, it breaks, and it leaves us staring upward, wondering what other walls might be out there, waiting to be found or dreamed into being. The Great Walls of Galaxies don't just reshape our understanding of the universe, they force us to confront fundamental questions about our place within it. Standing beneath the night sky, it's easy to feel small when faced with structures so vast they defy comprehension. But here's the paradox: these walls, while dwarfing our local cosmic neighborhood, might also be the very signposts an advanced civilization would use to navigate the cosmos. Imagine an interstellar society mapping their voyages not by stars, but by these titanic landmarks, treating them like mountain ranges on a cosmic trek. The Sloan Great Wall could be their Everest, the Hercules Corona Borealis their Andes monuments so enduring they outlast civilizations. This raises a deeper question. Could these walls be more than just backdrops? Some theorists speculate they might serve as cosmic resource depots, their dense clusters of galaxies offering abundant raw materials for civilizations mastering interstellar engineering. Picture a far future society harvesting stars from the Perseus-Pisces supercluster, or using the gravitational pull of a great wall to slingshot fleets of colony ships across voids. The wall's vast scales would demand technologies beyond our imagination, but their sheer concentration of matter makes them tantalizing targets for any culture thinking on geological timescales. Yet the humbling truth is that these structures also remind us of our fragility. The Milky Way is a speck within the Laniakea supercluster, which itself is a mere thread in a larger wall. Even if humanity someday spreads across our galaxy, we'd still occupy an insignificant fraction of these grand designs. That realization isn't discouraging, it's liberating. The universe doesn't care about our ambitions, our wars, or our borders. These walls existed billions of years before us and will persist long after we're gone. In their shadow, our differences feel trivial, our fleeting existence a footnote in a story written on scales we can barely grasp. Perhaps that's the greatest gift the Great Walls offer: perspective. They're both a challenge and an invitation, a challenge to think beyond planetary horizons and an invitation to see ourselves as part of something boundless. Whether they ever become navigational aids or resource hubs is beside the point. Their true power lies in how they expand our imagination, proving that reality will always outstrip our wildest dreams. And if another civilization is out there tracing these same filaments, they're likely staring back at the same awe, united across the abyss by the sheer scale of what surrounds us all. Want to explore the Great Walls of Galaxies yourself? You don't need a billion-dollar telescope, just an internet connection and curiosity. Projects like the Sloan Digital Sky Survey have flung open the cosmic vault, turning terabytes of galaxy data into public treasure anyone can dig through. Start with their free Navigate tool, a celestial GPS that lets you fly through three-dimensional maps of the universe, zooming past galaxies like a cosmic tourist. Here's how to begin your expedition. Open the Navigate tool and punch in coordinates for known walls. Try typing Sloan Great Wall to leap straight to its filamentary sprawl. The interface might feel overwhelming at first, but focus on these essentials. Redshift sliders let you peer deeper into cosmic time, while the density map overlay highlights where galaxies cluster into walls. Pro tip: adjust the galaxy type filter to isolate massive ellipticals. They're the skyscrapers of these cosmic cities, often marking a wall's densest intersections. For a real challenge, hunt unmapped structures. Download raw galaxy catalogs from SDSS Cache Job server, then use free software like TopCat to plot coordinates in 3D space. Look for suspiciously straight lines or dense planes, the hallmarks of a potential wall. Amateur astronomer Greta Aldrin, no relation to Buzz, made headlines last year by spotting a 500 million light-year filament near Pisces just by cross-referencing SDSS data with gravitational lensing maps from the Dark Energy Survey. Cloudy skies switch to virtual reality. Platforms like Space Engine or the ESA's Gaia Sky transform these datasets into immersive voyages where you can literally reach out and trace filaments with your hands. Crank up the simulation speed to watch walls evolve over billions of years, witnessing how mergers and dark energy reshape them. It's cosmic cartography meets time travel, no telescope required. The thrill isn't just in seeing known structures, but in realizing how much remains uncharted. In 2021, a high school coding club in Oslo discovered a dwarf galaxy cluster near the Coma Wall that professional surveys had missed, simply by writing a script to flag unusual star density patterns. Their find now bears their school's name in astronomical databases. That's the magic of this golden age. The universe's grandest designs are waiting, not just for satellites and supercomputers, but for anyone willing to look. So here we stand on a pale blue dot suspended within a tapestry so vast it defies comprehension. The Great Walls of galaxies aren't just structures, they're monuments to the universe's boundless creativity, each one a testament to the patient work of gravity and time. From the Sloan Great Wall's staggering filament to the ghostly embrace of dark matter weaving it all together, these colossal formations force us to rethink what large even means. They're not anomalies, they're the universe's grand design, written in the language of celestial bodies and empty voids. But the real revelation isn't just their scale, it's how they've rewritten our story. For centuries, we pictured galaxies as isolated islands adrift in nothingness. Now we know they're threads in a cosmic quilt, bound together by invisible forces into structures so immense, our fastest spacecraft would take trillions of years to cross them. And yet, for all their grandeur, these walls are fleeting. Dark energy's relentless pull will one day tear them apart, leaving future civilizations with a sky bereft of such wonders. We're living in a golden age of cosmic mapping, privileged to witness these titans before they fade into the expanding dark. That's the humbling paradox of it all. The same walls that make our Milky Way feel insignificant also grant us a front-row seat to the universe's most breathtaking architecture. From our tiny vantage point, we've decoded the echoes of ancient sound waves, traced dark matter's ghostly fingerprints, and glimpsed the universe not as a random scattering of lights, but as a living, evolving web. So the next time you look up at the night sky, remember, you're not just staring at stars, you're gazing at the distant contours of something far grander, a cosmic city whose streets are lined with galaxies and whose blueprint we're only beginning to read. The walls are out there, waiting to remind us how small we are and how extraordinary it is that we can see them at all.